Thanks, Scott, and welcome to today's webinar on designing PCBs for 2020 and beyond. Today's wireless product market is more competitive than ever. The development timeframe for RF designs is not only compressed, the market is demanding that these products cost less, are differentiated, and feature-rich. With 5G ramping up exponentially, designing RF PCBs that meet all of the performance, stability, and reliability requirements is critical for product success and meeting time-to-market target. The success of any wireless product requires a PCB design tool that makes the task of designing for RF-specific elements and their constraints easy. RF-centric PCB design capabilities not only ensure that products are top-performing, but also accelerate design time and reduce, even eliminate, design iterations. Design tool capabilities that support and accelerate the creation of RF-centric design like thermal and EMI analysis and optimizing power consumption are all necessary for RF products.
So, how Xpedition's PCB design capabilities can get you and your products a competitive advantage?
I'll turn this webinar over to one of our technical marketing engineers, Brent Klingforth. Brent?
Thank you, John. As you pointed out, electronic designs today need to be feature-rich, differentiated, and have the proper cost point. As the next generation of high-speed wireless communications starts to roll out, becoming mainstream around 2022, we will start to see it integrated into products like items we wear, products we use every day in our homes, to smart factories and monitoring devices in smart cities. Designers creating these next-generation products will need to adopt RF design techniques and start using application features they've never used before. As you mentioned, application technology that will help improve the quality of designs, dramatically reduce design time, provide additional integrations to third-party tools, and provide additional design verification will need to be added to our design flow, allowing you to meet cost and time-to-market targets. Let's get started by showing you why using a design application with true RF design technology like Xpedition will help you design in less time with higher confidence. Let's take a quick look at the product we're going to be working with today. It's a handheld infrared camera, and we're going to be replacing its current generation wireless communications board with a new high-speed version. While designing the complete product in NX, the mechanical engineer also created the board outline and mounting hole locations. We will then use this information to import to the PCB design tool. To get started, the mechanical engineer needs to activate the PCB from within NX. Open up the PCB Exchange application. We then need to publish the PCB, choosing the proper file format, IDX 3.0 for PADS Professional. We can set the file name and tag it as the base model, since this is our starting point. Click OK. Once the information has been exported, we get a quick report showing that the board outline has been generated and the mounting hole locations have all been created as well. With this completed, the PCB design engineer can now import the content into Xpedition. Before moving on to the PCB, we need to complete a couple steps in the schematic that we've left out. One of those is adding a connector that will connect this wireless board to the main board. To add this component, we're going to go ahead and use PartQuest. Once we've gone to the PartQuest website, we can use a search function to find our component. In this case here, I'm going to type in the part number for the component I found. This will narrow down our list. We'll get to see the components that are available to us. We can tell right away by the little icons next to the item whether or not there's a symbol, footprint, and 3D model for this component, in which in this case there is. Now that we've selected our component, we can drag that component into our search window in Xpedition Designer, and it will automatically import this content to our library. You can see once imported, our part will be there. We select that part. We can see the symbol and footprint. We'll then drag that symbol onto the schematic. Jumping ahead a bit, we have most of our connections placed already. We're just going to add a few more here. We're going to add a ground symbol to each side, and then we're going to connect the ground lines. After that, we're going to name 3 of the nets that haven't been named yet. From the Properties window, we can do that quickly by choosing from the drop-down list and selecting for each one of those items, ensuring that we don't have any misspelled errors. Now that we have the schematic complete, we're ready to synchronize to the PCB. So we activate project integration, and we'll choose the top amber light, letting the synchronization start. Immediately, we see a notification letting us know that there's a design exchange file waiting for us to import from the mechanical engineer. With the project now synchronized, we're ready to import the mechanical data that we notice we have an exchange file waiting for. Let's go ahead and click on the collaboration button. This will switch us into 3D mode, and the collaboration dialog box will open, where we can see the exchange file that's been posted by the mechanical engineer. If we choose that file, we can see the items that will be imported, the mounting holes, board outline, routing border, and such. Any notes that they've applied. We can go ahead and apply that to our design. And within a matter of seconds, we have our board outline with mounting holes. Let's go ahead and bounce back over to the schematic and look at some of the RF circuitry for this design. So here we're on the schematic page. This was actually brought in from Keysight's ADS. The RF engineer originated the design in this tool suite, so instead of us recapturing it, we used the automated connection from ADS to Xpedition to import the data content. So you can see when I click on one of the transmission lines from the schematic, I can view the parametric information like the length of the trace, the width of the trace. Now if we jump over to ADS, we can click on that same transmission line and we can see the parametric data that's in the schematic is the exact same thing in the ADS schematic. The RF groups we created in the schematic transferred over into the PCB. Right-clicking over one of these, we can use the auto-arrange function to automatically place each of the RF elements, simplifying the process of placing each one of the patch antennas on the PCB. As you notice, there's outlines around each one of the patch antennas. These are special design rules that you can create in Xpedition. For our fourth patch antenna, we need to adjust these rules. So by going to RF, Group Clearance Rules, we can see the 4 RF groups. Click on one of the groups, you'll see the rules that are created. For P4, I need to adjust the plane outline. I'm actually using this to assist with the placement. Now that we have the rules set for P4, let's go ahead and complete the placement. So you're probably asking where the patch antenna information came from. Well, since this was designed in ADS, the information was passed into the schematic, which automatically passed it into the PCB. Again, to show that the information coming from ADS to the schematic to the PCB is identical, let's go ahead and select one of the transmission lines and look at its properties. You'll notice that all the information is identical to what we saw back in ADS and the schematic. During design, there's always changes that occur. In this case, the RF engineer has decided they need to make a change to the patch antenna. So switching over to the ADS tool, the RF engineer will adjust the patch antenna shape. Once completed, the RF engineer can go to the Mentor DA menu option and choose Send ADS to Layout. This send from ADS initiates the RF mapping function from Xpedition, where we can choose the RF group that it's going to be applied to and set any other parameters that are required. Once we click OK, we can instantly see the patch antenna area update. In this case, it ended up adjusting the placement, so we just reselect the items and replace the patch antenna back in its appropriate location. With our RF elements placed, let's go ahead and place some of the components on the board. So using our Component Explorer, we've grouped the components together via the schematic. By selecting the PA group, we can see all of the components. We'll choose our power amplifier, drag it onto the schematic, and rotate it to its proper position. Going back to Component Explorer, let's place another group. This time we'll drag the entire group onto the board. If I right-click over the circle, I have several options for choosing to place components. In this case, I'm going to do sequentially. You'll notice as I place each individual component, the next one pops onto my cursor. After you're done, obviously you can adjust any of those parts as needed. As I place some of the smaller parts above the J4 connector, notice you'll see alignment markers. This is an option that can be turned on that will snap components from edge to edge. Our nets going from the PA to the patch antennas need to be 50 ohms. So to do this, we'll use our constraint editor system and click on Stack Up, where we can adjust various parameters to figure out our 50 ohm trace width. In this case, for the top, it looks like 10.4 mils. Now that we know this value, we can go and set the typical trace width to 10.4, and also see in the spreadsheet that it shows us the impedance of 50 ohms. Next, we're going to create a constraint class for the RF nets. So right-click over Constraint Class, choose New. We'll name it RF. Right-click over the name and choose Assign Nets. Then do a quick search for RX. Find all 4 of them. Add them to the group. We'll be using this later on for routing. Let's move on to routing our RF nets. This is where Xpedition has some special functionality that will help reduce the complexity of routing your RF signals. The feature we're going to use for routing these traces is the meander function. Holding your cursor over a button displays a video that shows you how to use this feature. This is a unique function within the Mentor family of tools. Once selected, a dialog box will appear that will allow you to set several parameters for how you want your meander or your RF traces routed. In this case here, we're going to taper down automatically to our 10.4 mil trace width. We'll route the other patch antenna on the far right. And then for the 2 in the middle, we'll use a special trace feature called Serpentine, where you can define the basic pattern prior to routing it. You'll notice as we route it in, it drops in that Serpentine pattern. We're using this because we know these 2 traces in the middle are the shorter of the 4 and will need to be matched. As we route into the BGA pins, all we had to do is guide it into that location. It will automatically pick up the center of it, and then we can drive it down into the pin with perfect alignment. To check the length on the RF traces we just routed, we can select one, right-click, and choose RF parameters. By selecting the one on the far right, which appears to be the longest one, we'll get our length matching value for the other 3. The 2 center traces already have their meanders added, so all we have to do is click on Edit Meander, and then we can select the meander section, and then we can push or pull it to add or reduce the length. The trace on the far left is going to require some special attention because we didn't add a serpentine to begin with. Luckily, we have a Add Serpentine option, so by selecting the trace, we can then right-click and choose Add Meander Serpentine. Now by simply clicking on the trace where we want it to start and end, we can pull a serpentine. With the RF Properties dialog box still open, we can click on each one of the RF segments we just routed and check the length. With some additional quick adjustments to a few of the segments that were a little short, we can perfectly match all 4 segments. Now that we have our RF traces routed, we need to add stitching vias around these traces. Normally this can be a very time-consuming process by placing one via at a time. To start, we'll choose the stitching via icon from the RF toolbar. This will open up the Add Via dialog box where we can set the parameters used to place our stitching vias. After which we can select all 4 of our RF traces. Next we'll set the net that we're going to use to ground, and then we'll set the distance between vias. Hit apply, wait a couple seconds. That one's not going to work for our needs. Go back and adjust our distance or stagger. So we'll undo it and apply again. This one looks much more suitable for our requirements. With a little bit of trial and error, we can converge on a solution, and then we can save that for future reference. Our next task is to stitch an area around the antennas, again based on a requirement that we've been given. So to do this, we've already created a plane area that we're going to use as our stitching area. We'll just turn our plane layer on, or turn our planes on. We'll then double click on that shape. In the Properties dialog box, we're going to choose a via stitching scheme that we've already defined. So very much like we did for the traces, we've just saved this off to a scheme and we can apply it to various shapes throughout the design. Once we've done that, we simply select on the shape, do right click, and choose Generate Stitching Vias. It's that simple. Just wait a few seconds and the plane area will fill in with the vias based on the pattern that we set up with that scheme. If we have multiple schemes created, we could undo this, choose a different scheme, and try it again. Now that we have all the components placed and some of the critical items created, let's send a file over to the mechanical engineer so he can review the placement with his mechanical. To do this, we'll activate the 3D scheme I've created. This will open up the appropriate toolbars. We'll then click on the MCAD collaboration. From our collaboration dialog box, we'll set the transaction type to proposal. We'll do a refresh. You'll see the dialog box fill in with all the components and RF objects that we've created. We'll then type in a note at the bottom as to what the proposal is for, and we'll hit send. Let's switch over to our mechanical engineer. He's been notified that we sent a file with component information. One of the advantages of using NX with the Mentor PCB flows is we export all the 3D model information, and that can be imported directly into NX, so there's no file mapping or part management that has to occur. So the mechanical engineer will now open up the PCB. He'll click on Import Incremental Data. The engineer will then see all of the objects being added, and we'll have the option to not import. In this case, we're going to go ahead and import everything that's included into the file. We'll go ahead and click OK. You'll see the models being imported and being placed into the design. When the process is completed, you'll get a report showing all of the component data that's been imported. We'll take a quick look at the board and notice that all of the parts imported, there are a couple models that we didn't have associated in the PCB that we'll have to work on at a later date. The mechanical engineer noticed a good portion of the board real estate was not being used, so the board outline will be modified to minimize real estate. So with the change occurring, they will output an incremental data set with just the board outline information that we will then update in the PCB. When a project integration is performed or you open up the PCB, you are automatically notified that a pending change is waiting for you from the mechanical engineer. Being notified of the change will open the collaboration tool. To assist with reviewing the changes, we can turn on the highlight feature. This will highlight those items in the PCB that are changing. So in this case, we'll notice the board area is much smaller than the original board area. If acceptable, you can go ahead and accept the change, which we will in this case. If not, you can reject the change and propose a different solution. Real quick, let's take a 3D view look at the board. So we'll spin it around a little bit. We can see all the components. We'll zoom in on the antenna area. You can see the stitching vias. We used blind vias in this case, a 1 to 2 via, because that's all we needed to get to the top ground plane into the next layer ground plane. We can turn the copper layer on to get a realistic view of what the board will look like in the end. On the mechanical side, we'll take a quick view as well. You can see the printed circuit board with all of the components in its current and final position. Let's recap what we just talked about. High-speed wireless communication will operate in frequencies 6 to 100 GHz. This will introduce design challenges most of us have never dealt with before when working with Bluetooth, Wi-Fi, or other low data rate mainstream technologies. Some of these new challenges will be using new PCB materials. Traces in copper require non-traditional shapes and rules like chamfered corners, trace tapering, precision copper shapes, using complex via stitching, in some cases PCB cavities, capturing RF elements at the schematic level, ensure proper design intent, integration with RF simulation tools, and importing proper shapes and converting to intelligent objects. As we've seen, RF design is far more than just picking a proper component. The PCB design is an integral part of the RF circuit in order for it to function properly. When using an application like Xpedition, we can design with confidence that our first revision will work as intended, saving time and money.